organically as you add or delete entries. Okay, so the next time you add a new entry, it will be using the third entry, the fourth one, so on and so forth. And let's say if you delete, let's say this is something. Okay, let's make it concrete. For example, let's say call it maybe ECE344. Okay, this could be a file or a subdirectory, right? So on and so forth. And let's call it a file, right? And you just append it, okay? As the order that you add them, if you delete one of the entry, so you create a hole. So the next time when you add a new file or subdirectories, it will be put here. Okay? That's typically how the OS implements the directory. Clear? Questions? All right, good. But the point is that you can't assume that there is specific order, which means that when you, let's say, for example, CD to a subdirectory or open a file, essentially the file system will need to scan every single entry linearly until it finds the matching name. Clear? Right? Okay. Well, the point is this, is that on Unix, because directories are treated the same way as a file, it's just, again, a directory is just a file with special format. What is special format? It's a list of name and location pairs. Okay? A file with name and location pairs. All right? So really, under Unix, we don't have system calls specifically to operate on directory. You say read and write that operate on a regular file to operate on the same of the directory files, right? But the library, standard library, they will provide some library functions to help you to easier manipulate the directory. Open directory, read directory, so on and so forth. But these are library calls, not system calls, okay? But on Windows, it's more explicitly supported. The system will provide system calls to manipulate directory, all right? I think we're all familiar with this. When you, for example, want to open a file, /1/2/3, let's assume this is a regular file, right? What happens is that the file system will start from the root directory, okay? And scan this root directory, the content, and finds an entry that costs 1. And it is a directory. And then based on the location, go to this directory content and search for an entry host 2. Similarly, and go to this directory, check its content, search for an entry that has 3. Okay? And then, because every name will have the location, we can find where this file called /1/2/3 is and open it. Okay? All right? So, again, the point is that it's a tree structure file system. Okay, that's how we find all the files. Okay, so now I think I should use the So now the question is that really, how do we do the map? How do we map a name, a false logical name, such as /1/2/3 to a particular disk location? All right. So what is our consideration? So first, similar to memory, the disk we can think of as a one-dimensional array, okay? Where each entry is called a block. Okay, let's say block 0, 1, 2, so on and so forth. All right, okay? Each block, how large is a block? 4K, right? So that is a typical size today. It happens to be the same as page size, so we can easily just swap a page into a block on the disk. Okay? All right? Well, this typically just assume 4K. Okay. Now we have this file. Okay? The file system needs to find somewhere on our disk and allocate this file to the disk. Right? That's a problem we are facing. All right? Now, how do we allocate? Well, first we need to find, for example, let's say this file is, I don't know, 10 blocks. Right? Okay? We need to find 10 free blocks. Okay? Now, the first question you want to ask yourself is that, do we put any constraint on these 10 blocks, 10 free blocks? Okay? What does that mean? We could find 10 consecutive blocks, 10 blocks that are free, and allocate this file. Okay? Or we just don't care. We don't care whether they're consecutive or not. Yes?
Sorry, a question. Is the file system a 1D array of blocks, or the file is a 1D array?
Huh?
Is the file system, like the whole disk,
Yeah.
1D array of blocks? Or is this file a 1D array?
This I'm talking about the disk. Okay, this is a disk. All right, whether it's an SSD or hard drive. To the OS today, it's just one-dimensional array of blocks. You index each block using the index. Just one single index. Okay, one-dimensional array. Right, that's essentially the interface exposed by the disk. All right, clear? All right. And it's, again, the OS job to allocate this file onto the disk. Okay? Back to my question, right? You have this file, let's say it has 10 blocks. Okay, it is 10 blocks. Do we try to find, what is our constraint? Do we try to, the file system try to find 10 consecutive blocks? Or no? Or, doesn't have to be consecutive. What do you think? Yes?
I think it will be best to find like 10 consecutive blocks, but I don't.
Why?
It's fast, right? If you want to access that file, then you can just load the next consecutive blocks and it will be shipped to the memory as soon as possible. You don't have to waste time to find the blocks. But I don't think it's necessary to find 10 consecutive blocks because like the fragmentation exists.
Okay. So first, you're right that if we can find 10 consecutive blocks, then it's fast, especially on hard drive. Okay? Remember, hard drive is this spinning thing, right? Typically, the blocks that are next to each other, they're located on the same track. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Roughly look like this, right? So, in order for us to read or write these 10 blocks together, okay, we only need one seek, okay, to put our arm here, and then wait until the first block, once the first block is under our read head or read or write head, then the next ones will just be read or written to consecutively. Right, one seek and one rotational delay to operate on 10 blocks. Clear? Right? But there's a big assumption. The assumption is that we assume the workload pattern we care about is you are going to operate on 10 blocks. You are going to write 10 blocks or read these 10 blocks. Right? Okay? That's a big assumption, right? For example, although the file has 10 blocks, every time I only just want to read one block. And then I'm going to read another file. And then come back to this file, and do another file, then we're really not saving much. Right? So ideally, the point is that because our disk has this seek time and the rotational delay, which are just mechanical overhead, very slow compared to CPU. Okay? So we are really optimizing. Now we're talking about layout of the file on this disk. We want to optimize the layout based on the workload. Okay? It is true that normally, most of the time, when you have multiple blocks of the file, they are going to be accessed sequentially. Okay, that's the workload. But you can always create a workload that doesn't do this, so that whatever your layout optimization is just useless under certain workload. Is it clear? Okay, but it is true that for most of the time you want to read all of them. Okay, in this case, it's better to allocate them sequentially so that they are really look like this on the disk. So one seek and one time rotational delay. Is that clear? Right? Okay. And if we can allocate this file sequentially on the disk, if you can always guarantee that, all right, then it will make our management easier, because all we need to keep track is where is the starting address of this file, okay, the start index, and then the length. Then we're done, right? And then the length, right? So for each file, we only need to keep track 2 numbers: the starting address and the length. All right? Okay, clear? All right. But it's impractical, right? That we cannot always guarantee a file is sequentially allocated. Because let's say we allocate 10 blocks here, because the file could grow, right? And then we allocate another file afterwards. Now what if this file grows? I want to add 1 more block, right? If we want to still keep our promise to say just sequentially, we have to move this file, right? To make some room, right? That becomes super slow. Okay, because we are talking about disk is slow and we are moving things around. A lot of code, right? Okay, so it is impractical. It is impractical for any file system to say, we're operating on the assumption that the files have to be sequentially allocated. Although all the file systems, later I'll explain, they will try to allocate it sequentially, but in the case, for example, if it grows, then it has to have a mechanism, a way to handle if the files are not sequential. Right? Okay, so far clear? Any questions? Okay. So if the file is not allocated sequentially, then it will make the file system's management job more complicated, because now not only we need to track more than the start and the length. Okay, in the worst case, every single block, they are just not consecutive. So the block A, I'll use ABCD to indicate the blocks, logical block of the file. It could be, A is here, B is here, C is there, so on and so forth. Right? They're just randomly allocated. Okay? So, if that's the case, we need to keep track the location of every single block of this file. Right? Okay? So that leads to the design of so-called index structure. Okay? It's called inode. Okay, inode. I stands for index. For each file, there is one inode. One and only one inode. Okay, now when I say file, it also includes directory. Okay? This inode, all right, so each file or directory has one and only one inode. Okay? This inode is pure overhead. In other words, it's not going to store the content. in fact, it is not visible to the user or the application. Okay, you examine the file, the content. Let's say this file has 10 blocks. Then really, to allocate it on the file system, we need to allocate at least one more block for inode. Okay, all right. What does this inode stores? Essentially, the index, the location of every single block of this file. All right. So the structure of an inode okay. So let's say an inode structure. It is a node, indicate it's one block. 4K. Okay, that's how large is it. At the beginning, it will have some metadata. Okay, store some metadata. What are the metadata like a permission? Who has what access to this file? The latest access time, the creation time, etc. Later I'll show you exactly what are the metadata. And then it has a bunch of pointers. It will have 12. This is called direct pointers. Okay, the next 12 entries. Okay? The next 12 entries are 12 pointers. It stores the location or the disk block address of the first 12 blocks of this file. All right, so this goes to block 0, block 1, and last block 11. Okay? All right? So for example, when we have a file that has 10 blocks, the 10 entries, 10 of these 12 direct pointers will be used. Each entry stores a disk address of that block. So if you allocate them sequentially, then these will be sequential. These addresses will grow sequentially, but still we keep track of every single block address. If we allocate them randomly, no problem. We have one entry for each. Yes, no question?
Yeah, I was asking about like if the are the pointers sequentially like pointing to the blocks.
Totally that's sequentially. So this is each entry indicates to the particular block. This is the first block, second block, so on and so forth. And we just need to store the block address. Okay. Is that clear? Any questions? All right. Now, what if our file has more than 12 blocks? Right? Now you could see we can keep using this heuristic and to store as many blocks as we can fit in this one inode, right? But that will be only give us limited number of blocks of file can contain. So the next 3 blocks, sort of special. 1, 2, 3. Okay. Use different color, right? This block has a special name. It is called single indirect. This block, the next one, is called double indirect. And the last one, what's the name? Triple indirect. You guys see it? You can see it, right? Okay. What does it mean? Okay. And that's it. Okay. And that's the end. You don't have more entries for the item. Okay. Each of these block here or entry here, it is a pointer. pointer to a disk block. So each of them will essentially take us. This will take us to a block. Okay? In this block, every single entry is a pointer. Okay? So this will be the 13th block, 14th, so on and so forth. Okay? So then let's assume that for each, okay, on 4 KB we can do the math, right? Let's assume 4 KB, that's the size of your block. And let's assume each pointer is what? 8 bytes, right? Each pointer, and we have 8 bytes per pointer, right? Then how many pointers can we store in a block? Huh? What is it? Anyone? No? Huh? 12, right? So we have 5, 12 pointers. Right? So the first 12 blocks, their addresses are stored here. Then from the 13th block, all the way to this 525 blocks, the next 512 blocks, their addresses are stored here. Okay? For example, how do I find the 13th block of my file? I go to the single indirect, take this address, go to this block, find the first entry. That is the address of the 13th block of my file. Yes.
To clarify, that's also in the disk.
Huh? That's also in the disk.
Everything is in the
Yeah,
disk.
everything here we draw is disk. Disk address. Disk block. Is that clear? Okay. So, and can you guess what a double indirect stands for? It is also a block, right? It is a block. Do I have another color? Let me see. I'll use red in this case. That take us to a block. And every single 8 bytes here, or word here, is a disk address. It's a pointer. But it's not a pointer to the file block. In fact, it is a pointer to a single indirect block. Right? Where's my yellow thing? Let's see. Oh, here. Yeah, thank you. And this will point us to file block. Okay? All right? So a single entry in the inode for the double indirect, how many file blocks can it address? 512 multiplied by 512. Okay? All right? Triple indirect, just 3 levels. So what is the total size, the largest file size under this scheme we can support? Is 512 multiplied by 512 multiplied by 512 multiplied by 512 plus 512 multiplied by 512 plus 512 plus. Okay, there's a limit. There's a limit to file size. Yes.
134,480,396.
Okay. So say that again. How?
134,480,396.
Yeah, 130 million. Right? 130 million, right? And times 4 KB. That is what? That is about 5. I think it's probably 512 GB. if my math is correct. Because this is KB, right? Okay. Roughly is this, the granularity of hundreds of gigabytes. Okay? All right. Okay. So that's the inode. Yes.
I wonder why, like the designs like this, like instead of like the page tables we are using in memory. Why won't you just use like single pointers?
Okay. If you're single pointers,
Like
then
the five, like single indirect pointers. Like we don't use like double indirect or triple indirect.
what do you mean? If you basically you have the so-called one level, then you have n. If you in total you need n blocks. In this case, 130 million blocks. You need 130 million entries, right?
No,
That's-
I mean like not single level, but like just make it double level instead of like triple levels. Why would you?
If you just use single indirect and double
Yeah,
indirect,
yeah.
well, then you have less files. You can support. You can only support this number of blocks, right? You can support too large of a file. Okay, make sense?
Why
Alright.
would you only have like one pointer to pointing to single indirect and one pointer pointing to double indirect? Like instead
What?
of like we have like 3 pointers all pointing to double indirect.
So there's no single indirect in your proposal. Is that what you're saying?
Yeah.
No single indirect. Everything is double indirect. What's important? Okay.
Cons is like it will spend more time to access
Exactly.
the files.
So what's the design philosophy here? We want to reward the smaller the file is, the faster the access. Right.
That's 512 gigabytes.
So that's for a single file, right? So I
Good
think
question. What do you think? You think it's not enough? Have
You can always
do you
split
have
the
a
files into like.
do you have a file that's larger than 512 gigabytes?
we can ask.
I mean, like possibly large logs.
A
large
log.
log.
Yeah, single log won't be this large. Okay.
Just a few megabytes large, like for very large log.
Have you seen a file that is hundreds of gigabytes?
We can always make up trash, right?
Huh?
We can always generate trash.
Sure. But the point is that the file system just doesn't support it, right? Okay. But this is actually, but under this scheme, right? This is relevant. Okay. You could, if you really worry about this, easily extend it to another level, right? I don't know, quadruple level, direct, right? It will grow exponentially, right? But today file system doesn't support that yet, right? But in fact, the modern file system, the inode, has another way. Okay, in addition to this index, okay, it will essentially mix an index with the start and offset. So this is called extend, right? Because today, for performance reasons, the file system still try to allocate these sequentially, right? Let's assume that most of the blocks, consecutive blocks in my file are sequentially allocated. Then using this index way is sort of a waste, right? So an extend essentially is a large sequentially allocated chunk. Okay? So today's file system is actually, the data structure is a mixture of index and the extend. Essentially, by each extend, we only need to start another. Right? So that can basically address much larger files, assuming that a big portion of it is sequentially allocated. Right? But everything is randomized, then that's still your limit. Okay? All right? Good. Any questions? But I want you to understand, right, what's the context here. So first, this is inode. It's not file content. For each file, there's an inode. Okay? And it's not visible to the user. Right? This is pure file system overhead. So in other words, you allocate a file, say 10 blocks. Your file system, overhead is at least one additional block will be allocated. And this happens for each file or directory. Okay? Right? And potentially, the overhead is not just one block. We could have these pointer blocks. Right? Depends on the size of your file. Okay? So there is overhead. Okay? You are using more disk spaces than the actual file content to manage the files. All right? Any questions? Now with this, then we essentially can now organize our entire file system. Our file system, I just talked about this is one file, right? Our file system, you have many files, but with this inode structure and the directory structure, we are able to organize them together on the disk, right? So the disk, typically the first few blocks of the disk are reserved. Okay? You can imagine you reserve what? What are the additional overhead? In addition to inode, what are the additional management overhead we need to store a file system? So yeah.
So say we have like many files, and so if we're creating a new file, we need to and we want to put the file in this block specifically, and we need to know if any file is using this block or something.
Right.
Or there must be some cases where we need to access. Maybe we store some map.
Okay. So the first block is typically reserved. It's called master block. We'll call super block. It stores some basic metadata information, such as the size of the disk, and if you are using different, this is just, I know it's just one format. For example, you are using, say you have different standard, you store all these things there, right? The total size, etc., right? And then it needs a data structure that across actually multiple blocks is called free map. Okay? Maybe multiple blocks called free map. Okay? As the name suggests, it indicates it's a bitmap to indicate for each block whether it is used or not, whether it's free or not. So it uses 1 bit to represent each block. Okay? So whenever we need to allocate blocks for a file, we just need to scan the free map, right? To see, okay, fine, give us where are the free blocks on this disk. Okay? Right? And then we can allocate for inode and file content. Right? And oh, by the way, for master block, it's very important for it to know where is the root directory. We need an entry point. Okay? So the root directory, master block. That will include the inode of root. Okay? We store the location of the inode of the root directory in the master block. Once we have that, then we can iteratively find every single file in our file system. Okay? So just imagine now, if you are going to access /1/2/3, what happens? First, from the master block, we locate the inode of root. Right? Okay? We locate the inode of root and take us to the inode, and it will take us to every single block, the content of the root directory. We go to each one of them and scan until we find an entry that costs 1. Right? So from the inode, locate data block, data contents, right? Root. And then we scan, right? The content will look like root is a special directory, but it's only special that it is the entry point, so that the inode location is stored in the master block. Other than that, it has the exact same format, so we scan, right? We scan until, let's say, we find an entry called 1. And by the way, now you could probably guess, in this name and location pair for the directory, what do we store in the location? Block address of what? Of what? What do we store here? Block address of the inode. Block address of inode. Is it clear? Okay. So we find this 1, all right? Okay, we find this entry, and it has, we look at the location. Let's say the location is, I don't know, let's say 12, right? What does it mean? We go to block number 12. For index by 12. What is this? What is this block? It is the inode, right? This is the inode of /1. Okay? So we interpreted the content of this block 12, treating as inode. Okay? And following each pointer, we go to the data content. All right? Okay. Inode. Inode location. Right? Okay? So in our example, it is 12, right? And then by following the inode, we locate the content of okay? So we go to the inode of this 1, right? We follow each pointer and find the location, and we do the scan. Looking for what? Looking for an entry that has, whose name is 2. Okay? Looking for an entry whose name is 2. Not 1/2, just 2. Right? 2 is the next level, the name of the subdirectory. Okay? So, search for an entry 2. If we do not find it, we'll say, okay, we can't find this file. Otherwise, we find the entry of 2. Okay, we take the location, and that will take us to the inode. The inode of 2. We repeat the same thing. Right? And number 5 is what? Is use the inode, right, just be consistent. Right? By following the inode, right, so locate the inode of /1/2, right? Which is a directory. And then follow the inode, we locate the content, right? content of this directory /1/2 and search for an entry. Entry. What? 3, right? Once we have the entry, we use the location. The location is what? The inode of 3. Repeat the same. And we can really find the content. Okay? Yes, you have a question?
Curious of how to represent the null pointer that we use 0.
Yeah.
Just make it point to an invalid address.
Yeah, exactly.
That's great.
Okay. Any other questions? Is it clear? How many you understand? Okay, how many you don't understand? Want me to repeat? Do you have a question? No? All good? All right. So, but I hope that this is simpler, much simpler than memory management. Right? Pretty much that's it. That's how we basically store the entire file system, map it to the disk, and find every single file and every single block. That's about it, right? Because now it's everything, all of these is implemented in software, in OS. You can change it, you can use a different algorithm. Okay? There's no hardware support whatsoever. Okay? All right. Just okay, so as another example, let's say we execute ls. ls is a file. It's a special file. It's an ELF file or executable file, right? So that you can execute it, but still it's a file, right? Now, when we type ls, right, really the file system will look for some directories in this path environment variable that essentially really locates this ls, /bin/ls, right? How do we do it? The same thing, right? We first, from the master block, we locate the inode of the root directory, okay? And we follow the first direct pointer, second direct pointer, scan the data content. This is the content of the root directory. That is the name and location pair. And search for the entry that has been, right? Once we find the match. What is this number? What is this? This is the address of the inode of this /bin, right? We go to here. This is the inode of this /bin. And the same thing, right? We follow the pointers to locate the actual content of this /bin, which is a directory. This bin is another directory, right? We look for the name that matches ls. Well, we find it. We take this number, 5728. What is it?
Address of the file.
Of the what?
Of the
This is the address of the inode of this /bin/ls, of this ls file, right? And then you locate the inode. We probably need to check all the permissions every time, right? From the metadata, and then we find all the content. The content are essentially instructions, right? Okay. All right. Any questions?
This
Yes.
is 32-bit address.
Why?
Because you only have four.
Oh, no, these are just examples.
Okay. And for the free map thing, what is the typical size for the free map?
You do the math, right?
Yeah, I try to do the math.
You use 1 bit to represent every block.
Which means
Right.
like I use the actual size of the disk and divide it by 4K. Right?
Divide by 4K for the divide by 8. Because
Oh.
that's byte, right?
That's still
That's still large.
well, yeah. We're doing the 8 now.
All right. But there's nothing you can do about it. Okay. All right. Any other questions? Good. Okay. Now, after you understand this data structure, let's think about how do you remove a file. First, how do you add a file? It should be trivial, right? Let's say, for example, Let's say you want to first, instead of adding a file, you want to append some write to this LS, append some blocks to it, right? What do? You allocate a new block and index it, add the index into the inode, right? Depend on, for example, if it only has 2 blocks, then you use the next direct pointer entry. Okay, but you potentially need to allocate a single indirect block, double indirect block, so on and so forth. But basically just add a block, right? So if you want to, let's say, for example, create a new file under the /bin, okay? Called new file, okay? What do? We need to add an entry here, right? Called new file, allocate an inode, and pointing this to the inode, okay? Essentially store the location as the block address of this newly created inode, and that's it. If a new file, if we haven't allocated the content, we don't need to allocate any content. All right? Okay? So that's how we add a new file. Is it clear? Any questions?
Can you repeat for the append? Because, from my understanding, if the file, because you use blocks to store files, right? But if the block hasn't, you haven't used up all of the previous block, why would you just?
Oh yeah, you're right. Right. Yeah, if this block is not all used, yeah, of course.
We
fill
start
it
from
up.
there
Right.
and then we have
Okay. All right. Any other questions? Okay. Now how do we remove? How do we remove a file? Okay. Remember that under Unix, the only system call available for us to implement the remove operation is called unlink. Why is it called unlink?
You just erase the pointer.
Let's say, for example, if you want to remove this LS, you say rm/bin/ls. That's how you remove a file, right? That's how you remove your memory. If you're not familiar with the Linux command, which you should by this point, just imagine you remove a file, delete a file, and ending up the operating system. What happens? What do you think it happens? Well, to you, is that now this file is no longer in the directory, right? Okay, after you call remove, this LS is can no longer be found by this bin directory. What do you think happens?
You just proceed to the phone, set pointers to the blocks.
Can you be more specific? Exactly here, let's say, if we want to say rm/bin/ls, remove this file /bin/ls. How do you change this picture?
Yeah. First, we need to actually find the LS, right?
Yeah, we need to find ls.
If
Very
it-
good. Okay.
And if we find LS, I think we have to clear. Should we clear the content? Because if not, what if the malicious guy get the block and still can access the contents of LS?
Okay, the question is interesting is that we need to clear the content, set everything to 0. Remember the OS is lazy, okay? They will do things lazily, it won't do things unless it's necessary.
So it only initialize if you want to use this garbage block.
Exactly.
Okay, I see.
All right? So what does it mean? What happens when you call rm/bin/ls? What happens? How do you change this picture?
The LS573 is the one.
This entry, we set this entry to null.
Should we mark that block as reusable block?
That's a good question. All right? That's a good question. But this is absolutely necessary, right?
Yes.
So that the next time you try to find this ls in this bin directory, it's no longer there. Right? Okay? So that's why it's called unlink. This system call is called unlink. Unlink it from the directory. Okay? So far, any questions? So you understand that we need to do this operation. But we need to do more, such as these blocks are really free now, right? We probably should return them to the system by what? In the free map, mark them as free, right? We don't have to clear them. Next time we allocate it, we clear it, right? Okay?
So what do you do, like mark all the structured blocks as well as the inode?
Yeah, we just essentially in that bit map, the bits that indicates these three blocks, the inode and these two data content block, mark the bit to be free. All right? Okay? Any questions? Now, first, you should realize, if that's the case, that's what the OS is doing. It means what? It means the actual content of the file we just removed is still there on the disk. And in fact, because we kept the inode, so we essentially only remove here, right? This is gone, right? This inode, these data blocks, including the pointers pointing these data blocks, are still there,
So it's still not safe.
right? So I mean by safe, depends on what you mean by safe. Okay, it means that if someone take your hard drive, scan every single block, it's very easy for this to find, okay, your inode will have a special pattern, right? You have metadata and then followed by these block pointers. You have a special pattern. It's very easy to guess this is an inode block. Follow the pointers and find this, reconstruct this entire file. Okay? So that is why data recovery from the hard drive is not hard. You can do it. Okay? Even if you remove the file, it's there. It's very easy to recover. That is why I forgot whether I showed you a video where you watch the video. If you really want to make sure you throw away your old computer, make sure no one can recover your hard drive content, physically damage it, right? That's the only way. Yes?
We can try to try to write new content sequentially throughout the hard
If you're super paranoid, you can do that, but that works on hard drive. Later when we talk about SSD, even that doesn't work. Okay? All right?
SSD, they try to write to the blocks frequently, very frequently.
We talk about SSD, right? So even that, okay, the point is that you're paranoid, okay? You don't just remove, you write a program to say, now I set this file, every single byte to be 0. And then you remove it. So you still keep the file structure, but the content is overwritten. It works on hard drive, not even on SSD doesn't work. Okay? Later we'll talk about it. All right? So that's the first thing to realize. Okay? That is why, actually, all the OS today, they have this trash bin. It makes very reasonably easy for you to recover the file, right? It's really pretty much free operation, right? When you remove this file, right, just remove this entry, but put this entry in the trash bin. Trash bin essentially is just another directory. I just put it there, right? Okay. So that's number one. Okay. And then you could think now, essentially, each file, when we say we put a file, right? For example, let's say you call move, right? You move this ls from /bin to another directory. Let's say, for example, a directory under user. What happens? Right? You move /bin/ls to /user. What happens? Huh? What happens?
Align an entry like ls.
It will just remove this and add this entry here. Right? Delete this entry, write this entry here. Do not touch any of these. Right? That is why when you move a file, it's very fast. Doesn't really matter how large your file is. Doesn't matter. we're not doing copying. We're not touching the inode, we're not touching the data content. We're just removing this entry and add this entry. Remove it from the source directory, add it into the target directory. That's it. Okay? Right? So now basically move is fast and remove is fast. Right? Okay? We're just manipulating the directory content, directory entries. Clear? Yes.
Give us what is LN, like the create a
We'll talk about that next. All right? Okay? Now, for example, if you use this, right? rm-r, what is -r? Recursive, it means remove everything. Right? Remove everything if it's a directory. It has subdirectory, remove everything. Recursively remove this whole subtree. Okay? What happens? What do you think would happen?
We'll start from the bottom, right? Like then it will be until it reaches the nearest.
Yeah. It basically start from the bottom and remove every single directory entry. But it won't break, it won't, for each file, the structure of inode and how it points to the data block, these won't be touched. Just essentially remove all these directory entries. Okay? All right? Clear? Okay? So that's file system. All right? So now there is this command called ln, create a link. Okay? Specifically, I'll show a demo. Let's see if I can connect to the still connection. There we go. All right. You guys can see it clearly, right? Okay. So I'm at one of the Linux machine, right? Okay. So I'm right now under my home directory, and there is a file in particular. Okay. There is a file under the OS 161 called the OS source. So where is that file? Did I remove it? I might have removed it, which is okay. So let's say, for example, now there's a file called ding readme, all right? It is this ding readme, right? This file is under the directory of OS 161, not under my root directory. Okay? Right? Okay? All right? So there is this command called stat under Linux. It will print out, you can operate on any file or directory. It will print out the metadata information. The metadata stored in each inode essentially are these. Okay? This essentially print out this information. And we can see that, for example, size, number of blocks, right? We can see there is this inode number. Okay? And it's something called a link. What do you think this link is? What do you think this number means?
Number of links.
Huh?
Number of links like pointing to this.
Number of links pointing to this file. At this moment, there's only one link pointing to this file, which means that there's only one directory containing this file, which is this OS 161-1.11. That's the only directory that contains this file. There is a command called ln, which stands for link, right? We could do ln. If we execute this, it will create a link of this file in this new target, in this directory, in our current, my home directory. So after I hit enter, okay, it's successful. I do ls under my current directory. You can see there, now this file is here. Okay? We just created a new file under my current directory. But create, when we say create, we are not duplicating the file. They're really pointing to the same file. Okay? Now, there's one file, one inode. We're not duplicating the file or the inode. but essentially we are adding this file into two directories, into essentially a home directory, right? So I can stat this newly created file. You can see that compared to the previous one, right? The inode is the same, which means that we are not creating a new inode or a new file, but the number of links now is 2. That means now 2 directories are containing, linking to this file, right? If we draw a picture, previously we have this inode. I'll use yellow as inode. This is inode of that file, okay? And this inode pointing to the content. The content doesn't really matter. Okay? Before I create a link, this is the directory of home OS161 1.11. This is that directory, right? The content, there is this entry called link read, right? And with some location, right? The location, in fact, it's nothing. Okay? So essentially, it points to here. Okay? This was a picture before. In the inode, there's metadata, so there's only one link. It's from this, from here. From this OS161-1.11. After we execute that command, we are essentially we are adding this entry to what? To my home directory. This is my home directory. Okay? Now we have 2 links. But both links, they are pointing to the same inode. Okay? Any questions? We could remove any of the link, right? For example, we can now remove it. If we remove it, what happens? We are essentially removing this entry, removing this link. But this file is still here under my home directory. Nothing changed, except the number of links are reduced to 1. The inode is still the same. Okay? All right? Okay? So we could remove, now if I further remove it, the file is really, we can't find it anymore. Right? So in other words, when I say when you remove a file, we do not just automatically mark the inode and the content in the free map as free. Because there could be multiple links. When we call remove, we are just removing one link. Only when the number of links reduced to 0, we can free them. All right? Okay? Yes?
Like, what if you're creating multiple links to this file and you change the file?
What do you think? Good question.
Then it is a soft link, right?
Oh, no. So nothing to. All these are not soft link. All right? Soft link is different. Now, if we change the file, what happens? If we have 2 links,
all of them should be changed.
All of them should be changed because there's only one copy,
Yes.
right?
Yes.
Okay.
What's the difference?
There's only one copy. There's no difference. There's no difference between these 2 links.
No, I mean like the soft link and hard link.
Okay, hold on. We'll talk about that. Okay. Any other questions? I just make sure I revert all my changes, move it back to the original directory. Okay. Okay. Any other questions? This link, right? You can create a lot of links on the same file. When you create a link, they are essentially equal. Okay. You have a question?
I'm just wondering what is the benefit for having a link command?
of the link command. If you want to really create a copy, that's essentially a shortcut, right? On the same underlying file you want to access in the very deep nested directory, and you want to have a shortcut, for example, from a desktop. Instead of copying it to our desktop, which takes time and will really waste space, create a link. All right? Okay? Clear? All right? Now, there is another thing called symbolic link or soft link. Okay? Now we are essentially the same thing, right? We give this -s option, it's called symbolic link, right? All the other things is the same, right? We just, inside of the default, it's called hard link, it's this kind of thing, right? We do this, right? Still, now you can see under my home directory, this ding.readme is here, but it's a special color. It uses special color blue to indicate a special link. It's a symbolic link. Okay? What is the difference? Well, this symbolic link, you first can see that it has a different inode number. The inode number changes, and the number of links is also is 1, right? If we basically stat the original file. You can see it's a different inode and different number of links. It's just 1 link. So what does it imply? It implies that, okay, this is hard link, all right? This is hard link. Implies that when we create a symbolic link, we are really creating a new file, a new inode. Okay? I will use red. Okay? This is a hard link. When we create a symbolic link, I'll use red. We are creating a new inode. This inode pointing to a file. It's a very special file. This file will further contain the information to tell you it's a link to this inode. All right? This is what happens. Okay? This is a special file and a special inode. All right? This file content is very special format. It's symbolic link. Right? What benefit does it have? First, now these 2 links are not equal. When we have hard link, these 2 links is equal. Sometimes you want to say, really differentiate, this is a special link. If I, for example, remove the original file, all the links shouldn't work. Okay? If that's your intention, in the hard link, you don't have that. If you remove, this is the original link, you remove it, the file is still there, it's still linked to the original, the newly added source. But under the symbolic link, if we remove this, okay, then this will become an invalid pointer. I'm pointing to something that has been removed. Okay? That's benefit number 1. But probably the biggest benefit is you can now, with hard link, you cannot link to a file that is on a different device. For example, you plug in a USB source, USB disk. Okay? So that USB disk has its own namespace, right? Has its own inode number, all these things. Okay? You cannot just say, I create a link across. This is a file on the USB disk, and let's say this is a directory that's stored on another device, that's your hard drive. You cannot create a link. But with symbolic link, you can, because here you can import more information to say, this inode is on a different device. Okay, you can do that. All right? Okay. We have to stop here. I have a meeting I can't get rid of at 4:30. Any final questions? Okay, good. You guys should try the stat, ln, move. Now you should be able to understand all these basic operations. ls, what is ls? Just go to the directory and print out everything. Right? CD, all these, now you should be able to understand. Okay, you should understand why, for example, copy is much slower than move. Right? Okay. Okay, and that's it. And you can pick up your term.
What's the average position?
I think 63 or something.
The higher.
And I think this time is probably harder than last year. So in the end, we probably means that we'll curve it.
Mine should be pretty full weight.
I should be at least 70 kg.
是交给谁来处理的？
I don't know.